Welcome back to an exciting day in Algebra 2. Today we are going to start our lesson on function transformations. So we are going to start by partially reviewing our parent functions that we learned last time and then looking at the transformations and how I can manipulate the equation and what that corresponds to visually on a graph. So I'm going to start just by going through and graphing each of these parent functions so that you get a good review of that firstly. This parent function, f of x equals x, this is our linear parent function. And some points that are on that function are 0, 0, 1, 1, 2, 2, negative 1, negative 1, negative 2, negative 2. 5 what are called key points or critical points are kind of your sweet spot for getting a clear visual on what's happening. So there's my linear function. Moving on to the next one, this is my rational parent function. And if we recall from last time, this one's special because it has a horizontal asymptote on the x-axis and a vertical asymptote on the y-axis. And then I've got my two curves in quadrants 1 and 3. Now this one doesn't have a whole lot of pretty points that are easy to graph, but I know in quadrant 1 I can at least graph 1, 1. And in quadrant 2 I can graph negative 1, negative 1. So I am going to use those 2 points, and then I can still go ahead and graph my curves. So there's our rational parent function. Moving on to the next row, this parent function, this is our cube parent function. Some critical points there, 0, 0, 1, 1, 2, 8, which is a little off the graph, but I want to try to eyeball it so I can get a clear picture of the shape of our graph. Negative 1, negative 1. And negative 2, negative 8. Same story about being a little bit off of our graph that we have here, but getting all 5 of those points gives us a clear shape. Moving on to the next one, this is our square root parent function. Some critical points here are 0, 0, 1, 1, 4, 2, and if I had a little bit more room, we could even go on to graph 9, 3, and I'll kind of, yeah, that's further off the graph. Moving on, when we see log, that means that is our logarithmic parent function. And this one was special because it has a horizontal asymptote at the y-axis. And this one also doesn't have a ton of pretty points, but we know it crosses the x-axis at 1, 0, and it is an increasing function. Then one next to it, 2 to the x, this is our exponential. And this one has a horizontal asymptote on the x-axis. Again, not going to have a ton of pretty points, but I do know it crosses the y-axis at 0, 1. And this is another increasing graph. Moving on down the line, the next one I'm looking at is my absolute value parent function. And we've got a lot of good critical points here, 0, 0, 1, 1, 2, 2. Negative 1, 1, negative 2, 2, and you could continue going, but for me, I've got enough, and I just want to make sure my edges are super straight. Okay, the one next to it, this is linear again. We had 10 graphs, 9 parent functions, so one of them was bound to repeat, but again, I can get those critical points. 0, 0, 1, 1, 2, 2, negative 1, negative 1, negative 2, negative 2. Moving into our last row, here we have our quadratic parent function. Some critical points there are 0, 0, 1, 1, 2, 4. If we had more space, we could do 3, 9. Negative 1, 1, negative 2, 4. And here I get a pretty good idea of what my parabola is going to look like on our graph. And then last but not least, we have our cubic or cube root function. Some critical points here, 0, 0, 1, 1, and it's off the graph, but I still want to be able to graph 8, 2, and then I've got negative 1, negative 1, and then 8, negative 2 again. This is going to help me to get a clear picture of our graph. Now, if you're ever unsure of what points are on your graph or not, you can always make an XY table where X is your input and Y is your output after you have plugged it into your equation. So, now that we have our parent functions on our graphs, we are going to look at these different transformations. When I take my function and add a number on the outside, that's going to be outside my parentheses, outside my absolute value symbol, outside of my radical, that is indicating a shift up. So if I have x plus 2, that means I'm going to take each of these points that was on my parent graph and shift them up 2 units. So what that does is it changes my y coordinate. My x's stay the same, and the shape of my graph remains the same. It's just on a different part of the graph. This just shifted up 2. Now, if you subtract on the outside, that would be still a vertical shift, but you're going to go down that many. So if I have 1 over x minus 1, that means all of this is going to shift down 1. So my vertical asymptote will not change, but my horizontal asymptote will move down from 0 to -1. And both of those critical points that I plotted will move down 1. So this will move to 1, 0. This will move to -1, -2. And then my graph will maintain its same shape, but we have just shifted it down. All right, moving on. If we are adding or subtracting inside of our parentheses, inside our absolute value, inside of our radical, that is going to be a horizontal shift, left or right. When you're subtracting a number, like here I have x minus 2 in the parentheses to the third power, that means I'm going to shift everything to the right 2 units. So that is going to change my x values only. I already did that one. And again, my graph maintains its shape. It is just scooted over. So if you are adding inside, like I have square root of x plus 3, and the plus 3 is inside my radical, that tells me I'm shifting to the left 3. And everything else stays the same. Now, if we multiply by a negative, that tells us to do a reflection. Where the negative is tells us which axis we're reflecting over. So if the negative is outside here, like negative log of x, that tells us to reflect across the x-axis, which means we're going to flip upside down. So for my log function, my vertical asymptote does not change. And our x-intercept is actually going to remain the same as well, but this graph is just going to be flipped on its head and now be decreasing. So it's a mirror image of itself vertically. If we move to the next one with a negative on the inside, that tells us to reflect across the y-axis. So here I have the exponential -2 to the x power. That means I'm going to reflect this over my y-axis. So my horizontal asymptote is not going to change. My y-intercept is not going to change either, but this graph is going to be a mirror image of itself and now be a decreasing function. Okay, the last type of transformation we're going to look at today are dilation. So we can dilate vertically, where we change our y-coordinate, and we can also dilate horizontally, where we change our x-coordinate. If you're multiplying outside, that's going to be a vertical dilation, and you are going to multiply your y-coordinate by whatever that multiplier is. So here I have 2 times the absolute value of x. That means I'm going to double each of my y-coordinates. Now 0 times 2 is still 0, so the vertex doesn't move. But 1, 1 becomes 1, 2. 2, 2 becomes 2, 4. Negative 1, 1 becomes negative 1, 2. Negative 2, 2 becomes negative 2, 4. So my x-coordinates did not change. We just doubled all of our y-coordinates. All right, another vertical dilation, 1/2 x. That tells us that we are going to halve each of our y-coordinates. Now 0, 0 is going to stay the same, but instead of 1, 1, I'm going to have 1, 1/2. Instead of 2, 2, I will have 2, 1. Instead of negative 1, negative 1, negative 1, negative 1/2. Instead of negative 2, negative 2, negative 2, negative 1. And so you can see when that multiplier is greater than 1, our graph got taller and more narrow. When that multiplier was less than 1, our graph got shorter and wider. So visually you can see what has changed depending on the value of your dilation. Okay, horizontals again are happening inside. And for horizontals, you're going to do the reciprocal of whatever the number is. So here, if I have 1/2 times x inside, that's what tells me it's horizontal. The reciprocal means you flip it upside down. So I'm not going to half each of my x coordinates. I'm actually going to double them. So on my parabola here, 0 times 2 is 0, but instead of 1, 1, I'm going to go to 2, 1. Instead of 2, 4, I'm going to go to 4, 4. I'm doubling my x-coordinates. Instead of negative 1, 1, it'll be negative 2, 1. Instead of negative 2, 4, it will be negative 4, negative 4. Or sorry, negative 4, positive 4. Okay. Now for a horizontal dilation where we have again a number in here, we're going to do the reciprocal. So I'm not going to multiply by 2, I'm going to halve each of my x coordinates. So 0, 0 will stay where it's at, but instead of 1, 1, I'm going to have 1 half 1. Instead of 8, 2, I'm going to have 4, 2. Instead of negative 1, it'll be negative 1 half negative 1. Instead of negative 8, negative 2, it'll be negative 4, negative 2. And so, again, visually, you can see when my multiplier was a fraction, a number less than 1, we got wider. When my multiplier was a number greater than 1, we got taller. And this one's a little hard to see just because of how cramped the graph is. But visually, when your multiplier is greater than 1, you are getting taller and narrower. When your multiplier is less than 1, you're getting shorter and wider. So on that note, we are going to look at just transforming some singular points. If I don't know what the whole function is, I can still complete the transformation. So if I have a point at negative 2, 5, and I'm looking at f of x plus 2. I don't even need to know what f of x is. I just know this means I'm going to shift up 2, and my coordinate moves to negative 2, 7. My y-coordinate increased by 2. If I have another unknown graph with a point at 3, 6, and I look at f of x minus 1, I don't even need to know what f of x is. I just know that means I'm going to scoot down 1, and the coordinates of this point are now 3, 5. My y value decreased by 1. If I have a point at negative 1, 4, and I'm looking at f of x minus 2, the minus 2 on the inside tells me this is a horizontal shift, and I'm going to go to the right 2. So the new coordinates there are positive 1, 4. My x-coordinate increased by 2. If I'm at negative 4, 3, and I'm looking at f of x plus 3, that tells me I'm shifting to the left 3. And so my new coordinates are negative 7, 3. My x-coordinate decreased by 3. Okay, for reflections, if I'm starting at 2, negative 4, and I'm looking at negative f of x, the negative on the outside tells me I'm going to reflect across the x-axis. So instead of being at negative 4, I'm going to be up here at positive 4. So 2, positive 4. The sign of my y value changed. My x did not. If I'm starting at negative 1, negative 2, and I'm looking at f of negative x, that tells me to reflect across the y-axis, which is going to change my x-coordinate to be positive 1, and then y remains negative 2. For these dilations, we're going to do a couple points so that we can visually see what is changing along the way. But if I have a point at 3, 1, 2, 2, and 1, 3, and I am looking at 2 times f of x, well, that tells me it's going to be a vertical dilation, and so I am going to double each of my y-coordinates. So these new coordinates are each going to be 3, 2, 2, 4, and 1, 6. Same thing for when we have a value less than 1. 1 half f of x tells me to halve each of my y-coordinates. So that's going to be 1, 1 and a half, 2, 1, and 3, 1 half. My x-coordinates did not change. And I'm just running low on space here, so I'm going to draw little arrows to the 3 I'm referring to. Okay, last but not least, horizontal, same story. If I am starting with 3 points, remember I'm doing the reciprocal here, so I'm going to triple each one. Quickly ran out of room here. And then last but not least, I have 3 more points. Reciprocal here tells me to divide each x-coordinate by 3. are my 3 new points with my 3 new coordinates.